Hey everybody, and welcome to our very first video lecture. I know things are a little bit weird starting out since we're definitely not used to this, but we'll muddle along as best we can, and I hope that things by the end of it will get pretty good. We're starting out with a review of triple integrals. This should be a really good review for us since we've taken maybe 1 or 2 weeks off so far, and it's a really good place to start because it should be pretty familiar ground given that we've covered it in class already. As you can probably tell, I'm dealing with working with a lot of new media, new software, so if an issue arises, please let me know. In particular, if you have any comments on things that you think could improve the video or improve your educational experience, please go ahead and send those my way. And with that being said, let's get on to the math. One thing I would like to mention though is as we go along, this new medium allows me to present information in a much more rapid format than we would do in class. So please bear that in mind and feel free to pause the video as you take notes or just consider what we're talking about. So our goal with triple integrals is to evaluate expressions of the following form. This is the triple integral over some domain E of a function of 3 variables, f of x, y, z, dv. This is our volume element. Our main tool for this is to rewrite the triple integral as an iterated integral. So we're rewriting these things as an iterated integral. The easiest example of this is when the domain E is just a box. So to start out, let's look at that example. So in this example, E is a box, and it's the collection of all triples of values x, y, z, so that x is bounded between 0 and 1, y is bounded between -1 and 1, and z is bounded between 2 and 3. And I'm taking a very simple function for f of x to start out with. I'm just going to integrate the function f of x, y, z equals x. So our goal here is to evaluate the triple integral over E of f of x, y, z dv. Just like before, we're going to rewrite this as an iterated integral. And this becomes the integral from 0 to 1, from -1 to 1, and from 2 to 3 of the function I'm integrating, which is just x, dz, dy, dx. And what we should notice here is that the order that I've listed things in this set, x bounds, y bounds, and z bounds, matches up with the order in the triple integral. The outermost integral is x, the middle integral is y, and the innermost integral is z. And we can check here. If I'm going to perform this iterated integral, I'm going to integrate this innermost thing first, which is integrating with respect to z from 2 to 3. And if I look in my box here, my bounds on my z value are from 2 to 3, so that matches up. My next integral after I perform the innermost integral is going to be the middle one, and there I'm performing this integral, and it's going to be with respect to y, which will correspond to these y bounds here, and I see that the bounds on that integral are from -1 to 1, so that also matches up. And then finally I'm going to perform that outermost integral, which is an integral from 0 to 1 with respect to x, and that too matches up with the bounds in x. So this is a nice way to double check and make sure that we've written everything appropriately. Now when we do this integral, I'm just going to integrate this innermost integral with respect to z. The integral with x with respect to z is just xz because I'm treating x like a constant. So this is the integral from 0 to 1, integral from -1 to 1 of xz evaluated from 2 to 3 dy dx. And this is what I'm going to plug this 3 and this 2 in for z. I'm going to get 3x minus 2x, so it's going to be 1x all told. So I have integral from 0 to 1, integral from -1 to 1 of x dy dx. Now I'm going to perform my next integral, and that's going to be integral with respect to y of x, which is going to leave me with the integral from 0 to 1 of xy. Again, I'm treating x like a constant because I'm integrating with respect to y. I'm evaluating this from -1 to 1 dx. So that's going to give me x minus negative x, so 2x all told. And this last integral is very easy to do. I'm just getting x squared evaluated from 0 to 1, which is going to be 1. So far our triple integrals have been very easy to do, but they can become much more complicated when E is not a box. So for for triple integrals where the domain is not a box, things are much more complicated. And then we have three main cases to worry about. Each case depends on the way that the domain is structured. In the first case, the domain looks like this. I have a strict limit from A to B, so my x values are ranging between A and B. And then my y values are ranging between some function g1 of x to some function g2 of x. And my z values are actually ranging between some lower surface here to some upper surface here. So the picture of my surface looks of my three-dimensional solid region looks something like this whole block here. This is all reflected in the way that we describe the solid region E in terms of a set. The set E is the collection of all triples x, y, z, so that x is fixed between A and B, y is fixed between that function g1 of x and that other function g2 of x, and z goes between that lower surface h1 of xy and the upper surface h2 of xy. And in this case, the triple integral over E of f of x, y, z dv can be written as this iterated integral, where the outer bounds are a and b, the innermost bounds are g1 and g2, and the middle bounds are g1 and g2, and the innermost bounds are h1 and h2, and I'm integrating f of x, y, z, dz, dy, dx. And again, we should notice that the bounds of everything match up. So in that innermost integral, I'm integrating with respect to z from h1 to h2, and that's exactly the bounds that I saw on my z term. For the middle integral, I'm integrating from g1 to g2 with respect to y, and if I look here, that's exactly the bounds that I'm seeing on my y term. And lastly, on that outermost integral, I'm integrating from a to b with respect to x, and that's exactly what I'm seeing for the bounds for my x term. And it should always be the case that your outermost integral bounds should be constants. So that's an easy thing to double check in your setup. And that's the first case. I want to think about here as well this region in the xy plane as sort of the shadow of my three-dimensional solid region E. So if I put a light up here and it was shining down on it, this is the shadow that would be cast by our three-dimensional region. So that concludes the first case. For the second case, things change just a little bit. Again, as before, I'm going from a to b in x, so that's not changing very much. But now, instead of going from a certain function of x and y to another function of x and y, I'm doing that same thing for z. So I'm going from g1 of z to g1 of x and z to g2 of x and z. And then in y this time, I'm going from this lower surface, which is a function of x and z, to this upper surface, which is a function of x and z. And this is again reflected in the set. My set is the collection of all x, y, and z values, such that x ranges between a and b, z ranges between g1 and g2, and y ranges between h1 and h2. And when I set up the triple integral, I'm going to use that same sort of format. So you can see my a and b bounds are my first integral there. My g1 and g2 are that second integral sign, and the h1 and h2 are that innermost integral. And when I integrate that innermost integral, I'm integrating with respect to y from h1 to h2, and that's exactly what my set says. When I integrate the middle integral, I'm integrating from g1 to g2 and z, and those were my z bounds. So that matches up. And then finally, when I do the outermost integral from a to b, that's with respect to x, just as before. Those are my x bounds. So just as before here, this inner part is the shadow that's being cast by my three-dimensional region. My region that I'm integrating over in the end is this solid region here, where I get everything. So everything inside this place. And if I were to put a light up above over here this time, and that light is shining down, this here would be the shadow that's cast by my region that I'm integrating over. So that's the case 2. Then finally for case 3, things change quite a bit. So in this case, I'm ranging between a and b in my y values, and then my z values are ranging between some function g1 of y and some function g2 of y. And then finally my x values are ranging between this lower surface here, h1 of yz, and this upper surface here, h2 of yz. So this is the range of my x values. And when I look at that solid domain that I get with this, it's this big chunk right here of including everything. So everything in between. So this is my solid region. And this is reflected again by the set. So this time y is ranging between a and b. I'm looking at all those x, y, z values where this happens. Z is ranging between g1 and g2. And x this time is ranging between h1 and h2. So x is sort of playing the role that z was before, and y is playing the role that x was before. And in this case, my triple integral is written as this iterated integral, integral from a to b, from g1 to g2, and from h1 to h2 of f of x, y, z, dx, dz, dy. It's important here that these variables match up. So this innermost integral is from h1 to h2. Those were the bounds in x. So that should match up with the bounds in x here. And yes, it does. The middle integral, going from g1 of y to g2 of y, is the integral with respect to z, and that should be the z bounds. And that matches up. And finally, the outermost integral is an integral with respect to y. So a and b should be the y bounds, and that's what we're seeing in that set as well. And this is a very similar idea to what we were seeing before. Again, if I place a light over here, then it casts a shadow. My solid region casts a shadow. And this is what this region in the YZ plane is about. So each of these cases can be distinguished by what sort of shadow we're casting. And oftentimes in a lot of problems we can use any one of the cases that we want to, and they'll all work okay. But some of them might be easier than others. So what we want to do is we want to typically make the shadow that we cast as simple as possible. So if I put a light in some particular place and I cast a shadow and I get like something that looks like a nice rectangle, that's going to be a lot easier to deal with than something that looks like some sort of crazy octagon or something like that. That'll be much harder to set up the integral over. But that's the end of case 3. And so far this thing has been a little bit abstract, so we're going to look at this through the guise of a couple examples. So in this example, what I want to do is I want to calculate the triple integral over e of some function, say f of xyz dv, where here e is the sphere of radius 1 centered at the origin. So we can set up this integral in a lot of different ways, and I'm not going to evaluate this integral because I'm not telling you what f of x, y, and z is, but my goal here is just to set up the integral. I just want to set this up as an iterated integral, and I'd like to set it up all the 3 different ways that we've talked about. So I think I can set this up in each of the 3 different cases. To start out, it might be really helpful to draw a picture of what we're trying to do. So let me draw some axes. And I'm trying to create a sphere of radius 1, which looks something like that. This is the light glancing off it. And this goes to 1, 1, 1. So let's think about that shape, and let's think about if I want to set up a region like the case 1, I'm putting my light up above it here and letting that shine down. and I want to see the shadow that it casts in the xy plane. In this particular case, the shadow that it casts in the xy plane is going to be also inside the body, and that's okay. It's going to be inside the solid region itself, but it's the shadow that we're casting here is really this circular region of a circle of radius 1 centered at the origin there in the xy plane. And we can even draw that region too. So I can draw a picture of the shadow, which is going to be in the xy plane. So let me draw some x and y axes here. And I've got a circle of radius 1. I'll keep the color consistent. It's a red circle of radius 1. And that's my shadow region right there. I feel like there's some sort of veiled Naruto reference that I'm missing, but this is my shadow region. Avatar? I don't know. Is there a shadow region in Pokemon? Well, we may never know. Now I want to think about the surface here that I've got. The surface, by the way, a sphere of radius 1 is given by this equation x squared plus y squared plus z squared equals 1. I want to think about this as an upper surface and a lower surface. So if I solve this for z, if I solve this equation for z, I get on the upper part z equals the square root of 1 minus x squared minus y squared. And when I take a square, I have a plus or a minus, and on the bottom part here, of course, I'm going to have z equals negative the square root of 1 minus x squared minus y squared. So that right away is going to give me my upper surface and my lower surface. And similarly, in the xy plane for that shadow, I'm going to have an upper curve and a lower curve. And that circle of radius 1 in the xy plane is given by x squared plus y squared equals 1. So if I solve this for y, I get y equals the square root of 1 minus x squared. And down below, of course, I'm getting y equals minus the square root of 1 minus x squared. So these are my upper and lower curves here too. This one being my upper curve, and then this one, of course, being my lower curve. So I can now write down an equation for the set E. E is the collection of all pairs x, y, and z, such that, and let's look here, x is going between this point and this point. This is the point -1, and this is the point 1. So if I'm looking at case 1, x is the one with the constant bounds, so x is ranging between -1 and 1. And y is ranging between this lower curve and this upper curve, so y is going between minus the square root of 1 minus x squared and the square root of 1 minus x squared. And then finally, z is going from this lower surface to this upper surface. So z is going between minus the square root of 1 minus x squared minus y squared and the square root of 1 minus x squared minus y squared. Once I have everything in this form with this set, it's very easy to write down the triple integral as an iterated integral. So the triple integral over e of f of x, y, z dv simply becomes the integral from -1 to 1, integral from minus the square root of 1 minus x squared to the square root of 1 minus x squared, and then the integral from minus the square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared of the function that I'm integrating, f of x, y, z. And then my order of integration should go, well, these were the bounds in z, so I should go dz first. That's the innermost integral. These are the bounds in y. The middle integral is the bounds in y, so it should be dy. And the constant bounds were x, so my outer integral should be x. So I've rewritten the triple integral as this iterated integral here. Now what I want to do is I want to repeat the same procedure, but treating it as if it were case 2 or case 3. So let's start fresh, and let me pull that picture of a sphere again. So there's my sphere in 3 dimensions, given by the equation x squared plus y squared plus z squared equals 1. And let's think about doing case 2. So for case 2, I'm putting my light over here and letting that shine, and thinking about the shadow that's cast, which in this case is going to be some shadow in the xz plane, and it's going to be this circle, again of radius 1 in the xz plane. And we can draw that out specifically in 2 dimensions. So I'm going to draw that circle in the xz plane. So let me make some x and z axes. And we'll write that circle again in red. Just a circle of radius 1. This is 1, this is 1, this is -1, -1. And in this case, my upper surface here is this right right hemisphere, rather. This is my upper surface. And then this over here is my lower surface. And I want to write down equations for both of these. So my right hemisphere is given by solving this equation, x squared plus y squared plus z squared equals 1 for y. And when I do that, I get y equals the square root of 1 minus x squared minus z squared. And if I solved it, when I take that square root, I'm going to have a minus as well, plus or minus, and that -1 is going to give me this other side, so y equals minus the square root of 1 minus x squared minus z squared. So that gives me my left and right hemisphere. And my region in the xz plane also has an upper curve and a lower curve. The upper curve is this one, and the lower curve is, maybe let's use this sky blue here. Blue skies and happy thoughts in these times, right? So the equation of the circle in the xz plane is x squared plus z squared equals 1. And that upper curve is given by solving for z, so it's going to be z equals the square root of 1 minus x squared. And that bottom curve is given by the minus sign, so z equals minus the square root of 1 minus x squared. Once we have all this information, it's very easy to write down the set E. So E is going to be the set of all points x, y, z, such that, again, for this case 2, x is the one with constant balance, and x is ranging between -1 and 1. So -1 is less than or equal to x, less than or equal to 1. And then z is ranging between this lower curve and this upper curve, so z is going between minus the square root of 1 minus x squared and the square root of 1 minus x squared. And finally, x is ranging between, y is ranging between this left hemisphere and this right hemisphere. So y is ranging between minus the square root of 1 minus x squared minus z squared and the square root of 1 minus x squared minus z squared. And once we have this description of the set E, the triple integral is very easily converted into an iterated integral. I'm just going to write the triple integral over E of f of x, y, z dv is equal to an integral from -1 to 1, so I'm just repeating the order of these bounds, integral from minus the square root of 1 minus x squared to the square root of 1 minus x squared, and then the integral from minus the square root of 1 minus x squared minus z squared to the square root of 1 minus x squared minus z squared of f of x, y, z dz dy dx. Now let me look here. Did I do this order right? dz dy dx was the order that we had before, but if I look here, I've accidentally messed up a couple things. So the first thing I messed up is that I already had the z bounds. I already had the z bounds right here, right? And I put z bounds again right here, and it doesn't really make sense for z to be bounded by z. So there's a typo right there, and that should have been a y. So let me go ahead and fix that. I'm going to put this in the shameful red color. This should have been a y. Very good. And then let's look at the order of integration here. So that innermost integral should have been an integral with respect to y. So this should be dy, because that was what the bounds were. And this middle integral were bounds in, or my bounds for z, so this should have been an integral with respect to z. And then this last integral should be an integral, of course, with respect to x. So that one's right. So let me fix all that up. And it's really good to double check right when you've written things down that everything's matching up appropriately. So that innermost integral is an integral with respect to y, so its bounds should only depend on the other two variables, x and z. And that matches up and makes sense. So this innermost integral checks out. The middle integral is this integral with respect to from minus the square root of 1 minus x squared to the square root of 1 minus x squared with respect to z, and those are exactly the z bounds, so that checks out as well. And then the outermost integral is the integral from minus 1 to 1 with respect to x, and those are my x bounds, so that matches up too. So this shows how to do this integral setup with using case 2 for integrating over the sphere. Now, I'll leave it to you guys to try at home. Try to set up that integral over the sphere using case 3. So your goal to try at home right now is to write this triple integral over e of f of xyz dv with e that sphere of radius 1 using that case 3 situation. And go ahead and pause your video right now as you try to do that. But the answer that you should get is following now. So the answer is the following iterated integral expression. To finish up here, let's try one more example where we evaluate a triple integral all the way through and where the domain is not a box. So let's consider the following example. Here what I want to do is I want to evaluate the triple integral over e of the function 6xy dv, where here e is this region that lies under the plane z equals 1 plus x plus y, and above the region in the xy plane bounded by y equals the square root of x, y equals 0, and x equals 1. Now a great way to start out in any of these problems is to draw a picture. This is definitely something that we were doing just before. So let's draw that region first in the xy plane. So let's have some x and y axes, x and y. Fix that up with a little bit of TV magic there. And I want to draw that curve y equals the square root of x, which looks a little bit like this, as well as the curve y equals 0. Y equals 0 is just the x-axis. Let me do that in red right here. And I've also got the curve x equals 1, which is that vertical line coming here. So my region is exactly this region, this red region here, where again this upper curve is y equals the square root of x. So if I were to express that region as a set, that region R here is the set of all points x, y, so that x goes between 0 and 1, and y goes between 0 and the square root of x. Man, we're very close. We're well on our way to describing the set E as a whole. And in order to describe the set E, all I need to do is tell you where z goes between. But the question itself tells us what z went between. Z went between this region in the xy plane, so z equals 0, and this plane z equals 1 plus x plus y. So the total description of the region E here, the solid region E that I'm going to be integrating over, is the collection of all tuples, or triples, x, y, z, such that x is between 0 and 1, y is between 0 and the square root of x, and z is going to go between 0 and that plane 1 plus x plus y. Now what we need to do is we need to rewrite this triple integral over e of 6xy dv as an iterated integral, and we just read everything off. So that set E says x is going between 0 and 1, y is going between 0 and the square root of x, and z is going between 0 and 1 plus x plus y. And I'm integrating the function 6xy, and this is dz, dy, dx. Okay, so the first thing I do is I calculate this innermost integral here. This is an integral with respect to z, so x and y are being treated like they're constants. So this becomes the integral from 0 to 1, integral from 0 to the square root of x, of 6xyz, evaluated from 0 to 1 plus x plus y, dy, dx. Now I'm plugging in these expressions in for z. When I plug in 0 in for z, I'm just going to get 0. So the only thing that matters is when I plug in 1 plus x plus y. And let me go ahead and skip a step and distribute that right away. So this is the integral from 0 to 1, integral from 0 to the square root of x, of 6xy times this thing. So I'm going to have a 1 in there, plus a 6x squared y, plus a 6xy squared dy dx. And I'm going to go ahead and integrate this last expression here. So I'm integrating now with respect to y, treating x like a constant. This is going to be the integral from 0 to 1. And when I get this, I'm going to have 3x y squared plus 3x squared y squared plus 2xy cubed. And this is evaluated from 0 to the square root of x dx. So this is then the integral, so this is going to be the integral from 0 to 1 of 3x squared plus 3x cubed plus 2x, it's going to be 3 halves plus 1, so it's going to be x to the 5 halves power dx. This integral is very easy to do, so this becomes x cubed plus 3 over 4 x to the 4th plus 4 over 7 x to the 7 over 2, value from 0 to 1. So our final answer is just 1 plus 3/4 plus 4/5. Oops, did I mess that up? Sorry, not 4/5, 4/7. That doesn't look right. 4/7, 4/7. There we go. Our nice, beautiful answer. And that should do it for now for us for our integral review for triple integrals. I'm going to recommend some more problems for you guys to look at for practice. It's a really good idea to practice more problems, not just the homework problems, especially because we're working remotely. So please go ahead and check out the problems in section 15.6, numbers 9 through 13. And I'll see you guys next time.